This is section 5.8, bond enthalpies. So what is bond enthalpy? Bond enthalpy is the enthalpy to break down a molecule into its components. So, for example, if you had Cl2 to break it down into 2Cl, you would need 242 kilojoules per mole, and that's the bond enthalpy. This can be represented as D, and then the parentheses, wherever the bond is. So in this case, it's ClCl. But if it were like CCl, the first one would be a C, and then a dash, and then a Cl. So this table is pretty much essential to solving any problems relating to bond enthalpy. This is the average bond enthalpy for most common bonds. You'll never need to memorize this table. You'll pretty much always have it in some form or another. It might be shortened to just the ones that you need for a problem, but you never need to memorize it. So this is the equation to find the enthalpy of a reaction using bond enthalpy. This is another way to solve for an enthalpy of a reaction instead of just the other formula. So it's the summation of the bond enthalpies of bonds broken minus the summation of bond enthalpies of the bonds formed. This diagram on the right here we'll do a practice problem that involves this diagram, but this can be used for a similar one could be used for any equation of this kind. Basically, when you break the bonds, that is going to require energy. So it's going to be a greater enthalpy. So you're taking energy to break the bonds, and then when you make the bonds of the new molecules, you will release energy. So the enthalpy goes down. So then this difference between the starting position and the ending position is going to be the enthalpy of the reaction, which is what this equation represents. So here we'll do a problem together. So this is our equation, but it's our formula, but it's separated into its bonds. When you see something like a CH3, that C is just bonded to each of those H's. So in this case, because the CH3 group stays on both sides of the equation, you don't need to calculate its bonds. So in this case, we have essentially these two bonds are broken, 1 mole CH bond and 1 mole CCl bond. And these bonds are formed, which is 1 mole CCl and 1 mole HCl. So this is C on the right, you break these two, and you're making these two. So here's the table. So the enthalpy of reaction. So you have your CH bond plus your CCl bond. So that's 413 plus 242. Your CCl bond and your HCl bond, 328 plus 431. So these are your bonds that you broke, and these are the bonds that you formed. You put those together, 655 minus 759. Your total enthalpy of reaction is negative 104. That is in kilojoules per mole. So in this scenario, this would be a exothermic reaction because it's releasing heat. This is a problem to do on your own. Here's the equation written out. You can see all the bonds that you need. If you have a coefficient like 2, you will just multiply every bond in there by that number. So take a few moments. You have the table to do it, and then I'll go on. Okay, so in this scenario, you have 12 of the CH bonds. So that's in here because you have 6 of them multiplied by the 2 out in front. You have 12. You have 2 of these CC bonds because you have the 2 out in front. 7 of these double O to O bonds, and then you're subtracting the bonds that you formed. So there's 2 OC double bonds, but you have 4 moles of these, so you have to multiply by 8 of those bonds instead, and you have 12 OH bonds here because you have 2 single, and you multiply by the 6. If you substitute these for the their bond enthalpy in the table, you will eventually add them all up, and you'll get 9,117 kilojoules minus 11,948 kilojoules for a total of negative 2,831 kilojoules. So in this scenario, that's its enthalpy of reaction, and it'll be an exothermic reaction.